Okay, so let me just first talk about what deform is, what we're trying to get to. So what's deform? And again, that's most places call that mechanics of materials. This is a class that's designed around trying to predict deformation and damage to materials. This is the example that I drew when we started internal loads in statics. But if you think of so that's supposed to be the back of a hand. That one's pretty good. Let's see how the other one goes. Okay. So say that you take your two hands and bend a stick. In statics, mostly what we did was figure out how to calculate the external loads on objects. So think about what a free body diagram looks like of this stick when it's bent. You have a force pushing up from each thumb, say F. And then you have a force, let's call it F, pulling down from the fingers. So a free body diagram would look something like that. Those are all the external loads on the stick. But you know that if you did this until it broke, the thing would break somewhere in here. And so obviously finding the external loads on an object is not a good predictor of where it's going to break. There's some other stuff going on determining where something's going to break besides where forces are applied to the outside. The first step towards getting at that information, why is it going to break there, is calculating internal loads. But even that, and I don't know, that's sort of an optional topic in statics, so I know some of you have had that and some of you have not. But what we did in statics, we calculated the internal loads, and that tells you a little bit more about where this is going to break. But even then, you could imagine, what if this stick, think of a cross-section of the stick. Okay, possible cross-section of the stick. Say the internal loads were really high right in the middle. Well, what if the stick in cross-section, it's hollow, but the walls get thicker here. What? Yeah, right, like a reverse of a bike frame, I guess. Well, then, even though you'd have high internal loads here, the thing most likely isn't going to break here because you've bulked up the material. It's stronger here. And so there must be something else going on deeper than those internal loads even that can let you find the place where this is likely to break. And so the external loads don't predict fracture. The internal loads don't predict fracture. So we need to go to stress and strain. And those are the two quantities that are going to let us figure out, no matter what the geometry is, where an object is going to break or where it's going to bend, how much it's going to bend. Stress is a measure of load, and strain is a measure of deformation, and they sort of go naturally together. You can think of stress and strain as being a pair, sort of the same way tension and elongation are a pair in Hooke's law and springs. And really that's what we're going to be doing here. We're going to be treating objects like sort of three-dimensional springs, where there's a known relationship between the loading and the deformation. Okay, let's talk about where deform is in mechanics family tree. Let's say everything starts with statics. That's most people's first class in mechanics. And from there you can go in two directions. You can go in this direction where we're talking about predicting damage. Or you could go in this direction, bless you, where you're talking about predicting motion. After statics, as far as predicting damage, the next class you take is this one, deform. That's you. And after deform, you can go into a very mathematical treatment of deformed topics, advanced deformed topics called continuum mechanics. Or you can go into a computer approach to these kind of problems called finite element analysis. FEA, or sometimes people call it FEM. Going in the other direction, predicting motion, you go to dynamics. And from dynamics, it sort of branches off into two directions. One is more solid dynamics. I'll call it advanced solid dynamics. And the other one is fluid dynamics. Bless you. In the direction that this class is in, going into the area of predicting damage, predicting deformation, the final line, it's sort of sad that this is the case. It would be cooler if it wasn't the case. But the final answer to everything comes from a numerical approach called finite elements, a computer approach. If you're really a good mathematician and good at continuum mechanics, you can do some pretty complicated problems, but you can't ever do problems complicated enough to be really useful in like industry or something. In the end, you always have to do a computer approach. It's a shame because people who are really good at math are cool, you know. So this is a question that might jump to mind when you hear that. If all practical applications use finite elements, use FEA, what do we want to get out of deform? First, we want to get an understanding of stress and strain that lets us, you know, finite element results are complicated. Making sense out of them can be complicated. So we need to understand stress and strain well enough to interpret these computer results. So understand stress and strain so we can interpret FEA results. And the second reason is just like when you do a complicated math equation, you try to look for ways that you can sanity check your answer, like does it make sense? This is negative 50. Does it make sense that it's that big a magnitude? Does it make sense that it's negative? We're going to learn ways that we can do simple problems that'll let us sanity check finite element answers, you know, because computer approaches to mechanics of materials, if you don't define the problem right, can give you garbage pretty easily, and you need to be able to notice and know when an answer comes up that is wrong. So sanity checking finite element analysis results. Anybody have any questions before I go on about kind of mechanics in general or finite elements or finite elements are, I mean, it's so cool. Like you can, I don't know how many of you have ever used like SolidWorks or Creo, but you build a thing in Creo, put a shape together, put some forces on it, do the finite element analysis, which isn't like trivial, but you know, once it happens fast, you can do it fast if you know what you're doing, and it'll tell you exactly where the stresses are, where the strains are on as complicated a geometry as you can imagine. It's amazing. Whereas like hand calculations like we're going to do, or even like advanced continuum mechanics allows you to do, you just can't do nearly the complexity of geometry that you can with this. Everything, you're always looking for planes of symmetry and all these things so you can simplify it enough that you can solve the problem. With finite elements, it can be as complicated as you want, and it still does it in seconds, you know.
It depends on what you're checking on too. We use
It does.
SolidWorks, and
It does.
sometimes it take hours.
Yeah. Well, that's just a lot of seconds.
Yes.
It's still seconds. No, you're right. But you can do stuff that you couldn't even dream of doing by hand. Okay. This whole class is going to be based on 4 simplifying assumptions. So virtually all of our calculations will require 4 simplifying assumptions. And I'll try to point out when things come up that don't require some of them, only require a couple of these assumptions. But for the most part, every calculation we do requires all four of these things. The first one is small deformations. That seems a little funny. That's why I don't like the wording of deformable body mechanics for this class. It makes you think that we're going to be able to do calculations with silly putty and pudding and stuff. All of the calculations that we can do are going to involve deformations much less than 1%, way less than 1%, 10 to the minus 4 and stuff like that. Let's say less than about 0.01%. Okay, so that's how deformable these bodies are. Not very deformable. Like if you have a 1 meter long bar, I believe that's 1/10 of a millimeter then, right? That we're talking about, and you stretch it out. We're talking about being able to stretch out a 1 meter long bar 1/10 of a millimeter. Okay, it's such a small amount, but for most engineering applications, this is a reasonable. This makes this applicable to most engineering applications. The second assumption is we're going to assume that there's a linear relationship between stress and strain. I mentioned this earlier. You've talked about materials before where there's a linear relationship between loading and deformation, springs, and that's what we have here. That was called Hooke's law in springs, and this is called Hooke's law also for materials. And in fact, the reason that Hooke's law is satisfied in springs is because Hooke's law is satisfied in the metal that springs are made out of. And all the spring does is allow a larger amount of deformation to happen before the material gets out of its linear range. So really the reason that springs obey Hooke's law is because they're made out of metals that obey Hooke's law. The third assumption we're going to make is that materials are homogeneous. That means that the material is the same at every point. So we won't be talking about calculations where you have little bits of one material suspended in another material. That would be non-homogeneous. We'll just be talking about a piece of steel or a piece of iron or whatever like that. And the fourth one, the last one, is that the material is isotropic. Homogeneous means the material is the same everywhere. At every point, the material is the same. Isotropic means the material is the same in every direction. There are some calculations we're going to be able to do for non-isotropic materials. For the most part, any material that has any kind of preferred grain, like a board, or any kind of material that's been made in a lab to have a certain what's it called? Direction of crystal direction, like a preferred crystal lattice direction. Those are not isotropic. They have one type of behavior in one direction and a different type of behavior in another. This came up, I think it was before you were at Twin Cities Engineering, but they were doing material testing of 3D printer material. And they found that the material, I don't remember which way, but because of the way in a 3D printer the plastic is laid down, it was about 10% stronger in tension going this direction compared to tension going this direction. So 10%. That means that it's not isotropic, but probably for a lot of applications it's close enough to isotropic that you could get some useful results out of this, but you'd have to be careful, you know. So that's the kind of thing that we're going to have to consider before we use these techniques. If what?
If it is homogeneous, can we say that?
No. So those are, it's tricky between these two things. It's a little confusing, but homogeneous has to do with at a point, take 2 points. The behavior has to be the same at those 2 points. Isotropic says, look at 1 point, look in this direction, and look in this direction, and the behavior has to be the same in those 2 directions. Any questions about that? That sort of brings up an issue with this stuff. All of this, like finite elements and mechanics of materials in general. Any of you who've taken circuits, there's just this incredible accuracy to the calculations that you can do. And so if there was a circuits, an electric version of isotropic versus non-isotropic, it would be a totally black and white issue. It either is or it isn't. You either can apply it or you can't. Mechanics doesn't tend to be that way. All of this stuff is somewhat approximate, and you're just trying to get in the ballpark. And so being off by 10% or whatever, like, yeah, you know, you have to think a little bit about what your application's going to be. There's no such thing as a mechanics calculation where you say, like, this is going to break when you apply 12,146 newtons, you know. All you can do in mechanics is say somewhere around 10,000, you better start to, you know, be concerned about the possibility. So it's very different in that way, and that it just reminded me of that when I said that about isotropy. Like, is it isotropic? Yeah, kind of. I don't know. Let's see. You know, that would really upset electrical engineers, but you kind of have to deal with that here. There's just no more precision than that. People use these kind of calculations for biomechanics calculations, bone strength calculations. Bones aren't even really a material exactly. Like, it's a porous structure. It has a preferred direction, but still, it seems like you get some somewhat meaningful results using these approaches, and so people use them. Okay. Well, let's take a 10-minute break, and when we come back, I'm going to get into mathematical preliminaries, which for deform is matrix math. So I'm going to talk about matrix calculations, and as soon as possible, you're going to want to figure out how to do these calculations on your calculator, because you are not going to want to do these by hand. Any questions about the stuff I just talked about? All right, let's start talking about matrices. Math background. Matrices. This is the biggest departure that I take. I mean, really, the only departure I think I take from the way this is taught in the textbooks that I listed and at the U, and I think any place that I've seen the format of the class, is that we're going to do all our calculations as matrix calculations. It's going to simplify things quite a bit, but you need to understand what these matrices mean. So we're going to spend a lot of time at the beginning setting things up in terms of matrix definitions, and then I think you'll find it simplifies things a lot. Everything that is given in the textbooks as 3 or 6 separate equations, we'll see as one equation, and that's the benefit of it, you know. And some seemingly really complicated equations, like why is this quadratic? It just comes naturally out of the matrix multiplication. So to me, it's a better way to do it, and that's how we're going to do it. So let's say that you have a matrix A. To represent this as a matrix, give it an undersquiggle. And let's say that this one is 2, 1. That's the first row. -2, 4, 0, 6. This is called a 3 by 2 matrix. The 3 is the number of rows, and the 2 is the number of columns, and it always goes in that order. You refer to the matrix elements as usually the matrix is given in uppercase and the elements are given lowercase. So you have like A, row number, column number is how you talk about which element you're talking about. So like A11 is the element in the first row, first column, so that's equal to 2. A12 is equal to 1. A21 is -2. A22 is 4. A31 is 0. And A32 is 6. In this class, there are 4 matrix sizes that we're going to deal with over and over again. You know, matrices can have any number of rows, any number of columns. So for this class, there are going to be 3 main matrix sizes. The first one is 3 by 3. That's the size of the stress tensor. And since stress is one of the main goals of this class is to understand the meaning of stress, this is a key one. So, for example, you write the stress tensor as the Greek letter sigma, under squiggle saying it's a matrix, and then 5 times 10 to the 6, 0. These are just literally random numbers around the size that you might see for a stress tensor. One thing to notice about what I've drawn here, and the units, by the way, are pascals, so like newtons per meter squared, or any units of force per area. So you could also do it as pounds per square inch, or kilopounds per square foot or whatever. Notice that the element 1, 2 is equal to the element 2, 1. The element 1, 3 is equal to the element 3, 1. 2, 3 is equal to 3, 2. Okay? So in every case, this stress tensor, if you switch the row number and the column number, you get the same value back. That doesn't have to be the case with a matrix. These could all be 9 different numbers. But that's, I'll talk about this more, but that's called a symmetric matrix, and all stress tensors have to have that symmetry. The second type that we're going to see a lot is a 3x1 matrix. That's any vector in 3D. So displacement vectors, force vectors, those are both going to come up a lot in this class. So you could have a force vector that's equal to 10,000, negative 45,000, 5,000. Units would be newtons. And that just says that the x component is 10,000, the y component is negative 45,000, z component is 5,000. So the first one is always the x component. Second one is the y component. And the third one is z. The third type that we're going to see a lot is 6x1. And we're going to use this to represent the Voigt form of the stress. So this is the stress tensor. But you can rearrange that. You know, instead of writing it as a 3x3 matrix, of course you could just list all those values in a single column if you want. Why would you? Why would you want to do that? Who knows? We'll talk about that more. But that would take 9 values, right? Except for that symmetry that says we don't need to know what 2, 1 is because we already know what 1, 2 is. We don't need to know what 3, 1 is because we already know what 1, 3 is, and so on. That cuts the total number of values down from 9 to 6 independent values. And so if you list all those independent values in a single column, you get a 6x1 matrix. That form's called the Voigt stress. And there's also, the strain is written in the Voigt form. So Voigt strain. It's named after the tremendous stress felt by John Voight's character in Midnight Cowboy. I assume. I don't really know that's true, but I assume that's the case. And then the last size that we're going to see a lot is 6x6. This is the stiffness matrix and also the compliance matrix. These are both used for the same thing. You can think of this. So Hooke's law says that with springs, the force applied to the spring is equal to a spring constant K times the deformation, right? This means the same thing. This is essentially the 3D spring constant that relates the Voigt stress to the Voigt strain. Okay, so those are the 4 sizes that we're going to use. You don't want to do matrix calculations by hand. You want to do it with a calculator. So here's how to enter matrices in your calculator. There are 3 ways. The first one is some of the older TI calculators have a matrix button. Like you hit the second function, go to matrix, then go to edit once you're in there, and it'll let you put values in a matrix. The second way is enter a single outer bracket for the whole matrix, and then inner square brackets, and then inner square brackets for the rows. So if you do open bracket, 2 comma 1, close bracket means that's the end of the first row. Then a second open bracket, -2 comma 4, close. Then open bracket 0 comma 6. That gives you the matrix 2, 1, -2, 4, 0, 6. And then the third way, this is my calculator lets me do this. Some of yours will, 2 of these ways will work fine and the other one won't, or whatever. But you can also do it as open square bracket, 2 comma 1, and then semicolon to change rows. So 2 comma 1, semicolon, -2 comma 4, semicolon, 0 comma 6. Close bracket, and that gives you the same one. So now let's talk about some things, some matrix calculations and functions. The first one is the transpose. So any matrix has a transpose. Let's say, let me change this a little bit. Let's say any matrix A has a transpose B, and the definition is the ijth element of B is equal to the jith element of A. So you get that by switching the rows with the columns. Here's an example. If the matrix A is 1, 2, 3, 4, 5, 6, then A transpose, and you write it with a capital T as if it's a exponent, is equal to, okay, so to get the transpose, you take what was the first row on this one and make it the first column over here. So the first column of this is 1, 2. The second row of A is 3, 4. So now that's the second column of A transpose. And the third row of A is 5, 6. So A transpose, that's the third column, 5, 6. now you can check a couple of these to make sure it works. So 3 is A21. For A transpose, 3 is, A transpose 1, 2. Okay, you get these values by just switching whether the subscript refers to the row or the column. It's built into TI calculators. So the way you would do this is define a matrix, however you do it on your calculator. And then use the store function to put that into a variable. And then you'd enter A, and then you'd go to the catalog and find this function. It just looks like an exponent, capital T. And if you type that in, it'll spit out the transpose of that matrix. Any questions about that? One thing that we're going to see a lot of is square matrices. And a square matrix, that's a pretty descriptive term. It just means you have the same number of rows as columns. So this is not a square matrix. But this is, let's say, 1, 3, 1, 2, 2, 4, 1, 0, negative 6. And for a square matrix, the diagonal elements are all the elements where I equals j, the column number equals the row number. So this here is 1, 1. This one's 2, 2. This one's 3, 3. So that's the diagonal of a square matrix. One important type of square matrix is called a symmetric matrix. And a symmetric matrix is defined by the matrix, let's call it M, is equal to its own transpose. Another way of saying that is Mij is equal to Mji. The stress tensor that I listed above is an example of a symmetric matrix. Symmetric matrices have a super useful property, and I don't know, probably everybody's heard this term before. I don't know how many of you have done this in classes before, but we'll get to it and talk about it in detail. But symmetric matrices have a really important property. And that is that all eigenvalues are real. There's no imaginary eigenvalues in a symmetric matrix. One thing to notice, and I mentioned this before, a symmetric 3x3 matrix, even though it has 9 elements, only 6 are independent. So a symmetric 3x3 matrix has 6 independent elements, and that's why the Voigt form of the stress only has 6 elements. There's no reason to list the other 3. It's redundant. Any questions about this yet? Any of this? Okay, so matrix multiplication. So matrix multiplication is just doing a series of dot products. So remember, a dot product, if you have a vector 2, 1, -2, dotted with -5, 0, 6. That's equal to 2 times -5 plus 1 times 0 plus -2 times 6. And what do you get there? -10, -12, -22. The input of dot product is 2 vectors, but the output is a scalar. And every element of the product of 2 matrices is a dot product. So every element of, let me write it as A, B, so that's A multiplied by B, is the dot product of a row of A and a column of B. Okay, so let's say I don't think the numbers I have here are right. So let's say we have a matrix 0, 1, 2, 3, 4, 5, 6, 7, 8. And we're multiplying it by a matrix 0. Let's do just all negatives. -1, -2, -3, -4, -5, -6, -7, -8. This is going to give us, this one's going to give us back a 3 by 3 matrix. This output matrix has, so let's call this A and call this B. This has the number of columns of A and the number of rows of B. Okay, so here are the, let's see, let me break this up into, okay, those are the 9 values we're trying to find. So to find this first one, we're going to take the dot product of the first row of A with the first column of B. So that's 0 times 0 plus 1 times -3 plus 2 times -6. What's that, -15? For the element 1, 2, we're going to take the first row of this one with the second column of this one. So we have 0 times -1 plus 1 times -4 plus 2 times -7. So that's -18. Any questions about this yet? Follow how I'm doing this? And then the third one, 0 times -2 plus 1 times -5 plus 2 times -8, -21. Well, they're each going up by 3. Why did that happen? Now for the second row, which row of matrix A are we going to use in the dot product? The 2, yep. And if we're trying to do the 2, 1 element, which column of B are we going to use? 1, yep. So 3 times 0, -3 times 4, 5 times -6, -42. Now for the 2, 2 element, we're going to use the second row of A and the second column of B. That's 3 times -1, 4 times -4, 5 times -7, so -35. What is it? 64?
54.
Oh, 54. So is the next one going to be 66? And then the last row, we had 6 times negative 2, plus 7 times negative 5, plus 8 times negative 8. That's impossible. Impossible to do with the human brain. What's that? Negative 12, negative 47 after you add that, negative 64, 111.
What did you just do, sir?
I'm multiplying this.
Yep.
Oh, what did I do?
You did row by row.
Oh, I don't want to do that.
I did.
I want to do this times this.
There we go.
Okay, so 0. Minus 21. Minus 48. Negative 69. So this is the orange one. This is the red one. Then negative 6. Negative 28. Negative 56. You guys do it. Minus 96? So what's that? 27 more?
88?
Oh.
Isn't it? The middle one? Just
Let's get these right anyways. I know that's not my usual style, but... Okay, so... Negative 90? Okay. And so this one... negative 90. And so then is it just 21 more? So negative 111. Okay. Here's another way to think about that formula. The element so if you have a matrix A and you're multiplying it by a matrix B, okay, and let's say this one is, let's say A is M by N, and B is R by S. And actually, that can't be. This has to be N by S, because this one has to have the same number of columns that this one has rows. Yes. So you can write that as the sum as I goes from 1 to N of A, and let's make this, let's change this to K. That's just a dummy variable. So A I K times B K J. And that gives you, you can think of that as the ijth element of the two matrices multiplied together. So in a computer program, this is how you would do it. You know, do a for loop over the k elements. Here are a couple important things. Oh, and how do you do this in the calculator? You create those matrices, and then you just use a regular multiplication. So in your calculator, you can go like 1, 2, 3, 4. Store that in the variable a. Have the second one be 0, 1, 2, 0, 1, semicolon, 2, 3. Store that in the matrix B. And then just do B times, let's say we want to do A times B. I don't know why they did that order. A multiplied by B. So you can see why these matrix approaches, you can start to see why these matrix approaches weren't super relied upon before calculators got powerful enough to do them and computers made it easy. It's pretty tedious to do this stuff by hand, but it's instant to do it on a calculator or a computer, and so we're going to take advantage of that. Here are a couple things to notice about matrix multiplication. The first one is the order of the multiplication matters, and you're not used to that with multiplication, so you got to keep that in mind. So that's the first one. AB does not equal BA. But grouping doesn't matter. That is AB, the quantity AB times the matrix C is equal to A times the quantity BC. And the third thing is you can't multiply any two matrices. The dimensions need to be appropriate, I guess. And we saw that with when I did this this summation notation thing. You can only multiply matrices that have the same number of columns in the first matrix and as the number of rows in the second matrix. Any questions about that? Okay, well, let's talk about what stress is. So the stress tensor. Say that you have a big chunk of material and you want to isolate a small cube of material inside there. What are the loads applied to the cube by the surrounding material. Well, there's 6 faces on that cube, and each one of those faces makes a fixed joint with the surrounding material. And so from joints, from statics, what kind of loads are applied to a body by a fixed joint?
Full force vector.
That's right, full force vector, and if you're in 3D, then a full couple vector too. So each face has a full force vector and a full couple vector acting. And remember what that couple is. We always treat it like it's a pure moment, but what it really is equal and opposite forces, a series of equal and opposite forces acting at a distance, right? So the smaller this cube is, the less distance there can be between those two forces applied by that couple, okay? So now, as we take a limit of this, should we do that yet? No, let's not do that. Should we? So yeah, as you take a limit of these loads, no, sorry, yeah, this is going to be better. Let's first let's represent those internal forces as force per area on that face. Okay, so we have so now if you isolate this cube, you have a force vector that we're representing as force per area acting there, one there, one there, and you have one on all of those 3 obscured faces too. And then we also have those couples. Now take the limit of these loads as the cube goes to 0 size. Or 0 length. couples disappear because those moment arms are getting smaller and smaller. So the moment arms are shrinking as the forces shrink. And so you're left with, I'm almost done, sorry, I'm going over. So what you're left with is an infinitesimal cube and on every face, the only loads acting are a force per area on each side. I'll call this, so if this is our coordinate system, x, y, z, I'll call this the force x divided by a. I'll call this the force y divided by a. Each one of those is a force vector. And I'll call this one the force z divided by a. Okay, so how many independent values do we have? Remember, there's three faces. There's three faces that aren't shown, but they're there, and they each have these loads acting too. Well, 6 faces, 3 components each face, so 18 total values. Okay. So 18 total force per area values. And what I'll do at the start tomorrow is we're going to get all the way from 18. So we'll reason down to 6 independent values, which is what I said stress tensors had before. But this is the origin of this is the idea that the stress tensor comes from. These 18 values of the force acting on a cube's face divided by the area of that face. Okay, that's it.